Okay, everybody. So today we're going to ask ourselves, okay, we have a data set. We can do all these really cool calculations on what percent of the population is, but all our predictions and all our calculations are predicated on the data set being normal. And in real life, no one's going to tell you your data is normal. You're going to have to look at it and say, well, is this data approximately normal? We'll never say that data is normal. Never, ever. It will not cross our lips, because any real data set is going to be approximately normal. And that's also a no-no on the AP exam. You can't say the data is normal. You can say the data is approximately normal. So we have really three methods of seeing if our data set is normal. Step one is to plot the data. That's one check. Two is we can check the empirical rule. Does it follow the 68, 95, 99.7? And step three is a newer one that we can use using technology, and we'll learn how to do this on the calculator, which is a normal probability plot. So we have a data set. Data set, we have 36 data points. It's the amount of cubic feet of a sample of 36 side-by-side refrigerators. It comes from Consumer Reports in the 2010 issue. You can go look it up if you are unbelievably bored and have absolutely nothing else to do. So, are the data close to normal? By the way, that last sentence would probably makes the English grammar guy in you go, like, what, are you normal? Shouldn't that be is, and why is that capitalized? But remember that data is a plural. So it's, we said, are the horses close to normal? That makes sense. So remember that it's datum is the singular. And people go back and forth on this and they fight about it because it doesn't sound right. But this is a grammatically correct sentence, is are the data close. And remember that normal is the name of the curve. It is a proper noun and hence always capitalized. So we have this data set. And if you want to put it in your calculator, you can. Pause the video, put it in your calculator, and assess it. Not necessary. So we have that data set. So how do we see if it's normal? Well, the first one is to plot the data. We're going to make a dot plot or a stem plot, preferably a histogram. If we're going to check if it's normal, histogram is preferable, and see if the data is approximately bell-shaped. Does it look, if we squint, does it look like a normal distribution? And then step two, sorry, we'll put this down here, is to check whether the data follows the 68, 95, 99.7 rule. Like, if we go one standard deviation away from the mean, is that actually 68% of the data? If we go two standard deviations away from the mean, is that actually 99, 95? And then if we go three, do we get almost all the data? And then we can do what's known as a normal probability plot. And this is probably the one that you're going to gravitate to, because it's fairly easy to do on the calculator and gives us a very good result. So here is the histogram of that data from the refrigerator. Use bin widths that make sense. Each bin is a half cubic foot, starting at 12.5, going to 19.5. And so we look at this and we say, is this normal? And so we kind of smooth through the tops, and it's close. It's pretty good. In a data set of 36, and when we get into the probability section, you'll see this. It's not always going to come out perfect. Just by random chance, we could have gaps because of our sample. So let's look at it. The next thing we can do is then the second step. And this is kind of the old way of doing it by paper and pencil, is we find the mean and the standard deviation of our data set. And in this case, we had a mean of 15.825 cubic feet and a standard deviation of 1.217 cubic feet. Always got to put your units on this so you have the context. So this is the average size of the 36 side-by-side refrigerators in the standard deviation. So on average, they vary about 1.2 cubic feet away from the center. So where does that leave us? So what we want to do is we want to calculate mu plus sigma and mu minus sigma. We don't have those because we're a sample. So we'll be using, we'll be approximating them with x bar and s sub x. Once again, we're not doing exact calculations. We don't know what mu and sigma are. We're approximating them with our statistics. So here are the calculations of our mean plus standard deviation, our mean minus standard deviation. So here the data set's in order. So where does this fall? Well, 14.608 falls there, and 17.042 falls there. And so now we count up how many points that is in our data set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that's 24 of our data points out of 36, which is approximately 0.67 or 67%. That's real close to 68. So really close to 68% of our population is between 1 and 2 standard deviation. I'm sorry, between 1 standard deviation above and below the mean. Remember that what we're saying is that at this point and this point, in our actual data set, we're getting something close to the 0.68 we would expect to be in this region. So we can repeat this process for 2 standard deviations away. And if we do that, we see that between those points, it's 34 of our 36 data points, or is approximately 94.4, which is what we'd expect. We'd expect there to be around 95% between 2 standard deviations above and 2 standard deviations below. And if we do 3 standard deviations, we actually get 36 of the 36 data points, which is 1.0 or 100%. But that's okay because that's really close to 99.7. So that's the second way. The third way we can check if our data is approximately normal is using something known as a probability, normal probability plot. And this is what is the best case scenario in the scientific community, but they generally didn't teach it in class because it was just really difficult. Is this axis, one axis is z-score, or I'm sorry, one axis is the actual percentage in the population, and then this one is what the percentage should be if it was a normal distribution. So this is the percentile rank, and this is the percentile of z-score in a normal distribution. But what's interesting is that if the normal probability plots lie pretty close to a straight line, then the data are approximately normal. Systematic deviations, a pattern, right? If we see a pattern, it's a non-normal distribution. So right here, if we see this pattern here where it starts above, it's not noise. There's a definitive curve pattern in here. If you see this, then it's most likely not normal. So let's look at our refrigerator data set, and we see this. We would see, if we created the normal probability plot, we would see that they form a nice straight line. And so we'll talk about how you do this in your TI-84 in class. But this is basically the ways that we assess if a data set is normal. So now we've finished the unit. There'll be another video tomorrow night, which is a test review video. But basically we've learned about in this section normal distributions, normal curves, the empirical rule, Right? Got to get this burned into your brain. 68, 95, 99.7. We've learned how a standard normal has a mean of 0 and a standard deviation of 1. We've played a little bit about the table, or we used the technology to do normal calculations, and we've learned how to assess normality. Is the data approximately normal? So that's it for today. I'll see everybody tomorrow. We're going to be doing a lot more normal probability calculations in class so that we really get the hang of it, and then we'll do a little exercise on assessing normality.